Hi, everyone. Make sure we got our slides going here. All right. Can I get a thumbs up or somebody?
Yeah, we
So,
can see it.
all right. Perfect. Thanks. All right. Okay. So we're going to continue our march towards figuring out how you make CT images. So we're going to do the math of how CT images are formed today. And this is kind of the core of, CT. What we're going to see today is how it's done, right? And there's some other, if it's hard to understand from the lectures that I'm giving here, it'll be really hard if you can't see anything. Let's plug that in. Sorry. Yeah. There's some other, there's many sources of back projection, convolution back projection lectures, etc., radon transform online, as well as other books. So here's a list, and it'll be in your slides. I'll put this up as a PDF for today's lecture. The PDF's not up there yet because I just rearranged slides because we've kind of fallen behind because of all the questions, right? So we're not going to cover as much material, but what I will do is I'll post some videos that demonstrate some of the programs, the MATLAB programs that are online in Canvas. So I'll just send that video out and say, here's how you use that MATLAB program, so that as opposed to going through it in class. Okay. But also these are very good textbooks. This one at the top here, if you're, hardcore CT technology person, want to know a lot about reconstruction, that's a very good textbook. Cack and Slaney is sort of I think it started in the 70s, I want to say. It's a really old, very basic textbook. So this is where we were on Wednesday. And recall, we figured out how to take our projections through this object such that we got the sum of mu1 and mu2 equals g1 here. Another projection of mu3 plus mu4 gives us another data point, g2, etc. We figured out that we needed this diagonal projection to get mu1 plus mu4. And then we just rearrange our data, as it were. These are our data points, G1 through G5 here. And we rearrange it such that it is, there's a large system matrix that says what mu values are added together to get that data point. And that will obviously depend on which ray you're passing through the patient, right? So each ray will have a different set of numbers here that tell you which mu values are along that ray. It gets to be a very big matrix, sort of 250,000 by 250,000. So it's hard to just directly invert it, right? And so one of the ways you can do a very naive back projection reconstruction of all of these projections that you've got is called naive back projection. And so what you do here for this example, we have a 3x3 image and the God-given mu values in this image are everywhere at 0 except the middle is 3. Okay, and so when we construct our projections, that we know what's under there, right? So when we do a projection through this top row, we get 0. A projection through this row, we get 3. And we don't know if that 3 is all of it's in here, all of it's in here, or some other way you can spread that 3 around in that row, right? We don't know that. All we know is the sum comes to 3, this comes to 0, and then we do these. And the diagonal ones as well. So since we have no idea in this projection which voxel this sum comes from. One potential way to do this is just spread that signal back across all of those voxels equally, right? Since we have no information about where it comes from, let's just put a 1 in each box. That adds up to 3. That's evenly spread across all of those mu values or voxels. So let's just do that, okay? And so our first step from that one projection is we make this subimage. And then what we'll do is we'll project back. What's the next one is this guy, right, along here. So we're going to put a 1 here, a 1 here, and a 1 here. There already was a 1 there, so that becomes a 2, right? And so we just sum that across there. And now we'll look at this vertical data here. We have 3 along here, so we'll spread a 1 here, a 1 here, a 1 here. Well, we had a 2 here, so that becomes a 3, right? And then we just keep doing that, just back projecting across the entire field. So 1, 1, 1, but there's a 4 here. Yeah.
Why do we add in the middle, knowing that the summation is 3?
Oh, because the thing in the middle. Oh, that's a good question, actually. So you're saying, why don't you normalize it such that it all comes out to 3 as you go?
The first step I understand,
Yeah.
right?
Yeah.
Step, we already know that the diagonal
adds
up to 3, so I don't see the point of us adding
a
2 in the center.
That's a very good point. In that this would add up to 4, and so you're already so you could just normalize it such that it add up to 3. So let's just do that. We'll change the slide for next year since you pointed out an inconsistency here. We could just, normalize this so that it came back to 3. However, this isn't the way to reconstruct, but it is a naive way to reconstruct, right? And you get something in the end that looks happily kind of like the object, right? It is not the object. It is not the correct answer, but it's got some of the features of the true underlying object. Yeah.
Voxel the v value, and then you're adding up the voxels like in a specific row, and that's what you call a projection.
Correct. Right. This is sort of a toy problem to show what naive back projection is. We have the algebra of naive back projection is in the book, right? And we'll get there and we'll take a look at it. So if we have, say, a disk in the plane and a projection of a disk looks something like this. It's 0 where the disk is not. And then when we start integrating down through the disk, it rises up to a peak, right? When we're going through the thickest part of the disk, and then it goes back down to 0 on this side of the disk, okay? And say we take 3 views of that disk in the plane and we back project those in a naive way, we get something that looks like this. And we know from these projections that, hey, there's only one thing in this field of view, basically, and it's a blob right here. So you know something about what's going on. You've created a picture that is not the object at all because it has all of these lines in the background, which aren't there in the true object. But let's say we clicked through these angles at a much finer resolution. We did 1,000 projections and we back project all of those. Well, then all of these things start just adding up to a background haze, right? And we get a picture that looks something like this with this background haze. And we get something that has a peak, like it has a profile that looks like that. It's got a peak in the middle, right? And it's kind of blurred out. So that is not a disk in the plane, right? But it's a function that sort of has a peak right where the disk is centered, etc. Let me, okay. Oh, doesn't want to go back. Okay, so what actually happens is we get values of all these projections from one view of the patient, and this turns out to be projections from one view of a patient's head. Okay, so this is along basically this direction here is along the direction of the detector, right? And what we're going to do is take that number and just spray it back all the way through the plane. However, this is done with what's called convolution back projection. And we'll see as we change the angles and add more projections in, the object comes into view, right? As you add more of these projections in. And so if we look how that evolves, you can see with the first few projections, right, they're coming in this direction, obviously. We have virtually no information about edge structures around here, right? Because you're projecting through them, through the edge. However, this edge is quite well resolved, like where that edge is, and that's because your projections are tangent to that edge, and you're either seeing nothing, or when you move one detector element over, all of a sudden you're seeing bone. And so now you've got a very sharp boundary, right? With just a few projections, you see this feature, right? However, we don't see any features along this way. We need to get the angle of projections in that direction to start seeing features here, okay? And then as we add more projections, we get more features until we go all the way around and we basically have reconstructed the two-dimensional object. This is called convolution back projection. The way we got rid of all of the stuff in the background and everything, we're going to figure out mathematically now. And it's the way CT has been done for about 40 years or something like that. It's this convolution back projection algorithm. To get going, we will look at what's called a sinogram. And it's GL theta. If you recall, the G's were the projections, L is the direction of our detector, and theta is the angle. And so this function here is the GL theta function. It's a two-dimensional function of these projections. And so here's our object that this sinogram was created from. And theta is in this direction, up and down, and L is in this direction, which is along here. So the question is, if I see the object and I see the projection, and you can just take a second and say, well, what projection through this object where I add up all of the mu values in some set of parallel directions, what is the angle of adding that up in order to get the data along this point in GL theta? So recall, this is a specific theta value, right? And this is, as I move along, I get different values in L on my detector, right? So you can see a few features of this as theta changes, right, up and down. Like as I move up and down, theta changes, right? So I'm looking at different views of this object. And we can see a large boundary in here, which is moving like a sine wave, right? And so this is the outside boundary of this main thing in the field of view, right? So when this is maximum, right, that boundary is as wide as you can go, you kind of know just from common sense that my parallel lines for the projection are coming down vertically, right? Because that would give you a projection that is the widest along L, right? And then if I go 90 degrees to that, right, then these sides move in and the main, signal in the projection closes into a minimum, and that would be either this minimum or this minimum, right? When I'm looking left to right, when my projection is left to right. So you kind of get the picture of how this would work. If you look at other individual features, we have two very dark circles in here, and you look at the sinogram and you can see where they are, right? One's here, right? As we're changing theta, it's oscillating back and forth along the detector where it's projected. And this is the other dark circle oscillating back and forth on the projector, right? As I'm rotating around. So we also have in the background of these projections, this schmutz over here, right? So this looks like air, right? It's got no absorption there. This looks like some kind of complex thing, right? Outside the main body of the phantom. And so that is all this junk down here. This is the table, right? So when you have it, there are small features here, but when you project through them, right, you're going to see those features in your projection. And so that's here, and that's also over here. So let's say this is small L up to big L. This is detector 1. This is detector 892 or something like that, right? So small L to big L. That would mean which one of these lines is my detector for this projection. So I've set my theta, and that's what we're going to try and figure out. We're going to try and figure out which theta am I talking about here. Is it this theta, so that my large L is over here, my small L is here? Is it this theta such that my small L is here, large L is here? We can kind of rule this one out, right? Because if I project perpendicular to it, I project onto that detector, I would be at one of these widest points, right? So it's not that one, and it's not this one, because that would be true for this one, right? It's actually at one of the minima. So it's either this one or this one, right? And if we say, this is convention, this is small L here, and this is big L, and big L is the end of the arrow, we'll say, then it's probably this one, right? Because all this junk is right here at big L values. And so that would say I'm looking at this projection here is the integral of this phantom all the way down this way, right? So I went camping at this super dusty place. I got, took my kids camping. I don't know if you camp in California, but you should, if you go, you should wear jeans and cowboy boots because you're just like, it's just dust. Everywhere is dusty. It's like, like you just walk to the fire and this dust thing comes up. It's crazy. Yeah.
I just had a question on this. So if you, can you also tell it's like that projection, the projection, since it's like, hitting that like table on the right edge right there of the first image?
Correct. So if this is big L and big is like, this is the origin of L, this is 1, this is 800 down here, then all of this stuff is being projected down here on that side. Now, the interesting thing is that if we look at this one, right, this projection D, well, that would be this up here, right? And are they any different? They're just flipped, right? That's it. So there is a symmetry in these projections, right? In that once I reach theta equals pi or 180 degrees, all I have to do really is just say, well, let's just flip L to minus L, and that's my data, right? So if we have parallel beams, all I need is 180 degrees of data, because if I keep going and get 360, I'm just resampling that data, right? We'll see that there's some fine structure in CT that makes that actually not true, but mathematically it's true. Yeah. Yeah, I would say if this is my detector, I would imagine the X-ray source to be over here and beaming through the object and then hitting the detector this way. So the data, if my detector's over here, there would be little scintillators on the detector right there. There'll be like 800 of them lined up this way. Mathematically, we're only going to look at parallel beams. And so the way you can do that is you can have a X-ray source that rasters from here down to here and pushes parallel beams through the object. Right? Yep, the theta is the angle. So this theta here, this is we can call this like 90 degrees, right? And then, the theta here, if we call that, so that's 90, right? Depends how we want to label things, like which direction theta would go. But this could be minus 90 degrees, right? If this was 0. This degree here is 0, then I would flip down like that to minus 90. Yeah. Right. Okay. And then here, for this angle, if we're projecting through the object this way, this is a special point because this is where those two circles intersect, right? And so now they're essentially in this projection, they're overlapping. And so you get an extra dark or point here because the two circles are in that beam, right? So that's how sinograms work. I'll give away the punchline. If I have a dot in my object, it is going to create a sine wave in the sinogram, right? And that sine wave, they all have the same frequency, right? Because they're all, going around at, 0 to pi or whatever. So each sine wave has the same wavelength, but its amplitude and its phase changes depending on the position of that dot, right? So we won't go through the MATLAB code today, but there's a way, very simple program, you can put dots in and see what the sinogram looks like for dots and play around with it. Yeah.
What's the relation between like sinogram and the back projection?
Oh, we're gonna find that out. Yep, that's what today's goal is, to find out like how you turn a sinogram into an image through. We'll find out we have to do convolution back projection. Back projection gives you those fuzzy images. So here's a more complex object, right? And a more complex sinogram. Now it's hard to follow individual sine waves, etc., because the object has many features. And so they all start overlapping and summing up, and you get a much more complex function over here. As you can imagine, a human being is pretty complicated in terms of the pattern on this side. And so the sine wave or the sinogram is much more difficult to interpret than this. But this is the fundamental sinogram. If we do naive back projection, and this is called a laminogram. I don't know why they name it laminogram, but that's what it's called. But you can just call it naive back projection. If this is one of our views, okay, and so this is in the detector direction this way, right? Theta, as you can see, is set somewhere around 45 degrees, and we're just going to project all of those signals back onto the plane. And we're going to create a two-dimensional function that is, has x and y, right? All x and y's are here. And this is a picture of that back projection at the angle theta. And so this is our GL theta, is how it's related to GL theta, in that we have an expression here for L, right? Remember when we said all the points along this line here are essentially parameterized by this function. It's every x and y along this line. So it's just a line in the plane that satisfies these 2 points where L is one parameter and theta is the other. So if I have this, now let's say I have 1,000 of these at different thetas. I can add up all of those continuous functions, and here they are. I'm just going to add them up from 0 to 180 degrees, and the sum of all those looks something like this, right? So it looks like the object, right? We have these dots where the dots are supposed to be, but the dots are kind of blurry, and there's a huge amount of signal in the background that doesn't exist in the actual object. Okay, so the laminogram is a way to get there, but we need to do something to fix this, right? So I will go through I'll post up a video of going through this little MATLAB script. It's like, I don't know, 50 lines long or 20 lines long or something. And it just demonstrates this is a very simple sinogram because you have like point objects, right? And when you have all of these voxels filled with different objects, this becomes a more complex, function. So let's look at the math. In the textbook, we have this notation. We're going to move from this notation to the notation we use in the course in a couple of slides. But when you're reading the chapter on the projection slice theorem, this is what you're going to see. If this is our two-dimensional object, this is our person or our potato or whatever we're imaging, and these are the parallel rays of X-rays going through the object, creating a function GL theta down here, okay? A very interesting phenomenon occurs. If I take the one-dimensional Fourier transform of this function GL theta, right, it turns out that is the function here at the same angle that goes through the Fourier transform of this function. This is called the projection slice theorem. So here's my function. Now let's take the God-given continuous 2D Fourier transform of that function, put it over here. I now integrate these sums through this function or project values down onto a single axis through that function. Take the Fourier transform, the 1D Fourier transform of this thing. So this is a spatial variable L. This is a spatial frequency. And what that's rho here. And along that angle, I will have sampled the Fourier transform of the object. I don't know, does that seem like a natural thing? Doesn't, does it? To me, it's quite miraculous that actually happens, right? Because you're taking all of the detail of this object, well, at least all the detail in one direction, and just adding it all together. You're blurring it as much as you can actually blur something by just integrating it all, right? And putting it on this point here. And then, however, when you take the Fourier transform in the orthogonal direction, right, you are sampling the spatial coefficients in the Fourier transform in that direction. I can say it as many times as you want, and it still doesn't seem to be something you go, oh yeah, I could figure that out. That's true. It just doesn't fall out, right? So here's the algebra, right? We're not going to go through it, but this is Jerry Prince goes through it here for us and shows that it's true, right? And this is called the projection slice theorem. It's absolutely fundamental to CT. It only takes 4 lines, and it's just basically substituting variables to pull out the fact that this is the Fourier transform, and it actually works. It's true, and so you get the final step here that the projection slice theorem works. So you can go through those. We've fallen so far behind. We're not going to go step by step through that. So here's for these proofs here. For that proof, you want to be in this basically notational system. Okay. We have our GL theta is represented down here. In this course, this is how it all is. All we've done is change some letters here, right? Just change some labels. Our object is mu, which is the linear attenuation coefficients in the object, right? As a function of position, that's our continuous object. GL theta is this projection. L is the same, theta is the same. Over in Fourier space, we will call big U is the Fourier transform of mu xy. So this is the Fourier transform of our image, and it is in Fourier space, which is indexed by wave number or kx, right? Kx, ky. So these are in cycles per centimeter, and this is in, say, centimeters. Right? In the Fourier space, we can also, this is its continuous 2D transform as a function of kx, ky. We will find it very useful or necessary actually, in the next couple of slides to actually express the Fourier transform of the object in polar coordinates. And that makes sense because by this projection, this is in polar coordinates, right? So this is what's happened. We've got an angle here sampling through that. So our natural sampling of the Fourier space is in this polar coordinate system. So we're going to express this Fourier transform in polar coordinates. And this is the projection slice theorem written as algebra. And so it says, here's our data, GL theta. This is one projection and a set of samples along our sampling grid. We take the Fourier transform of that as a function of L, right? So theta doesn't change. It's just a parameter. We do the 1D Fourier transform. We get G, which is the God-given Fourier transform of little GL theta. Big G K theta is the Fourier transform of our object, and we've sampled it, along this direction, right? Theta is just a parameter there, right? That's the projection slice theorem. You can do a few examples to reassure yourself that this works. The projection slice theorem works. You can just like put a function and know its Fourier transform and make sure that, basically if you project through that function, you get a line projection through the Fourier transform, right? So one simple way of doing it is with one of the functions we've used a lot so far, which is like the sinc function and the rect function. So here's a very simple rect function. If you project through here, right, we're going to get a one-dimensional top hat function, right, as we go through here, right? And that tells us that along that projection angle, if I look at the Fourier transform along that ray in Fourier space, I will get the sinc function that corresponds to the rect function here in 1D, right? More complex is that so here's, you can go through this algebra. It's not that hard. A more complex thing is if you say, now I'm going to test this hypothesis at 45 degrees with the square, right? So let's go back here and we'll say, let's test it like adding this way. So I'm going to put my samples along this line with theta 45 degrees, and I'll integrate down through this. And so now I don't have a simple rect function anymore, right? With that integral, I have a triangle function, right? And so we can look and see, is the Fourier transform of the triangle function the thing that is along this direction, right, in the Fourier transform? And you can prove that to yourself that that's true. Okay, so one way of doing it, some of you, if you're jumping ahead in your brain, you say, well, wait, I've got a GL theta here, and I've got a set of these that I've measured at different thetas. And I'll take each one and I'll just take its Fourier transform, and it'll map a line through the Fourier transform of my object. If I do that for a lot of different angles, now I have this sort of, it's basically a polar coordinate sampling of that Fourier transform. One cheap way of reconstructing it, perhaps, is to interpolate this function, these points that are in polar coordinates, onto a rectilinear grid in Fourier space. So I have these sampled points. They're not uniformly sampled in rectilinear Fourier space, right? They're sampled on all of these lines. But I could interpolate them over onto a grid and then just do a 2D Fourier transform, and a discrete Fourier transform to get the image, right? That's one way of reconstructing it. Turns out it doesn't work 100% of the time. There are reasons why this projection slice theorem, in reality, with hard data that you get on a scanner, it's not exactly the projection slice theorem like perfectly. And so it will give you artifacts when you're trying to interpolate this onto a rectilinear grid, and you'll get artifacts in your picture. But that's one way of doing the reconstruction. Another way of doing the reconstruction is sticking with your data, right, that you have. And so we've converted all of our measurements. We have a whole set of GL thetas. We take those one-dimensional Fourier transforms, and now we have a whole set of rays through the Fourier transform of our object, right? And we want to take this and figure out what, our object looks like, the mu values. So we know that mu xy, which is our object, is the inverse Fourier transform of big G, right, as a function of, that is the Fourier transform of little g. And so this is the equation to do that inversion. So this is the inverse Fourier transform of big G to get back to mu, right? If we're going to, instead of doing it by making this function, which we don't have, we have this function, right? We've sampled this function. So in order to use this function to do an inverse Fourier transform, we have to do the inverse Fourier transform in polar coordinates. Well, it's just calculus, right? So here's the equation for the Fourier transform. And just using integral calculus, we're going to say, well, what does the Fourier transform look like in polar coordinates, right? Because we have this thing in polar coordinates. And so we'll change the variables. Kx will be k cos theta, ky will be k sine theta, and then the absolute distance in Fourier space from the origin, or k, will just be kx squared plus ky squared square rooted, right? So that's just going to polar coordinates. That's all we're doing here. However, when we go to polar coordinates and we're doing an integral, we need to use the Jacobian for polar coordinates, right? And recall how the Jacobian for polar coordinates goes. It's r dr d theta is the Jacobian for that transformation, right? And so here, in our notation here, k is equivalent to the r, right? So we need to put the Jacobian, which is absolute value k dk d theta, okay? We'll look at, the reason you can use the absolute value k is that we have this symmetry such that, g of k at theta plus pi, when we go all the way around, is the same as g of negative k, right? So we really only have to integrate from 0 out to pi with k, and go around, with theta, and then do this integral on absolute value of k, okay? So here's our new integral, right? This is the inverse Fourier transform to get this. So let's look at this thing here. So here it is again, written out. We have, we can take basically the absolute value of k, push it over here such that now all of our k dependent stuff is inside here, right? And this looks like the inverse Fourier transform of a product, right? And the product is k times the Fourier transform of our object, right? Or of GL theta, which is this big G k theta, right? So we can perform that. So we'll perform this, right? 1D inverse Fourier transform first. And that gives us a new function that is now dependent on L, because we've done the inverse Fourier transform, right? And it's parameterized by theta. So we set theta here, right? And the integral is not dependent on theta. So I now have a new function, and we're going to call it G star little l theta, which is equivalent to this guy, right? So let's take a look more closely at G star, this guy, G star little l theta. So here it is. That's just taking this thing and putting it down here. If we look at this, it's the inverse Fourier transform of a product. And this is why we spent time on the convolution theorem, right, for the Fourier transform. So if I have a product here, I know that the Fourier transform of this product is just the inverse Fourier transform of gk theta, which is this, convolved with the inverse Fourier transform of k, or magnitude k, right? So that's what we're going to call that thing. There it is. The inverse Fourier transform of k. And so now we have GL theta, which is our original data, remember, that we measured, convolved with this thing, which is now a function of L, right? And that thing is the inverse Fourier transform of K. So this guy here, when we look at it and we recall back to that formula about making back projections, this is basically a back projection, right? We're just going to add up all of these things that are at different theta values, right? And so we're just, instead of doing a back projection of GL theta, we're now going to do a back projection of this G star L theta, right? And that's the difference, right? Back projection of GL theta produced that object that was similar to, but was not our object. Back projection of G star L theta will produce the object, right? And the difference is G star L theta is our data, GL theta, convolved with this thing, right? So this is by the convolution theorem. This, remember a few slides ago, we had that back projection was just the integral of all those b thetas xy over theta. That's essentially this guy right here. Right? So there's two ways to go about this then, given our data that we've measured. So here's our data in hand. It's the sinogram for GL theta. And what we'll do is for each projection in there, for each theta, we'll look along L. We'll do a convolution with the inverse Fourier transform of the function absolute value of k. What is the function absolute value of k? We should look at that and say, what does that actually look like in Fourier space? What's its value at, say, the origin? So it just goes down to 0, right? And as k goes up, it just goes up linearly with k, right? So it's basically, it just goes up like that, right? So it's just y equals x, right? Or y equals magnitude, right, of x, and just goes out like this. So it's a very simple function, right? Take its Fourier transform, you get something that looks like this. Yeah.
In time domain, in space, in spatial domain, the Fk has infinite energy,
Mm-hmm. That's a good question. We'll look at that. Yeah.
Frequency domain looks like it has finite energy, as it is sinusoidally of decaying now.
Right.
Exponentially decaying, so it looks like it has finite energy there. So
yeah. So the question is, does the function the inverse Fourier transform of k, is it bounded? Like, does it have finite energy? Because it sure would seem that this function in the Fourier domain does not. It goes on forever, right? So we have to make a choice. We have to cut it off at some point and say, okay, that's as far as we're going to go out, and do a finite interval, right? So we'll take a look at that. We'll have a diagram to look at that. Okay. So getting that order the algorithm here, we're going to take our raw data that we've just taken off the scanner, we'll convolve it with the inverse Fourier transform of k. And then that'll give us a set of these functions, and we'll back project those to get our image, right? Another way of doing it, and this is where your question comes in, is let's look in the Fourier domain using the projection slice theorem. We go through and look at a sample through the Fourier domain. We multiply it, as we did in that formula, we multiply it by k, okay? But we have to cut it off at some cutoff point. You know, normally the function itself will roll down to 0. And so after that, there's no point in multiplying by k. The whole thing rolls down to 0 anyway. So we've got some maximum spatial frequency that we're going to worry about and cut it off. And then here's our ramp function. Okay. This is often called a ramp function because it, looks like a linear ramp, right? Or the Rom-Lock function after the two guys who came up with this method of reconstruction. So we multiply those things together, just like in the formula on the previous page, right? So here it is. We just multiply here, right? And then we take the inverse Fourier transform of the product, right? And that gives us the filtered back projection, the same thing, the G star L theta, right? And back project those. So you can go through the Fourier domain to do it and do the multiplication and then the inverse Fourier transform, or we can take our raw data and convolve it with the inverse Fourier transform of that K. Either pathway is fine. Normally this is done for years, this was done on scanners. So let's take a look at what it looks like. So remember we had GL theta of a disk looks something like this, right? When we integrated down through a disk, we got a function that had nothing outside the disk. And then as you moved through the disk, the integral got bigger and bigger until finally you were at the diameter of the disk, which is maximum. So you got a maximum here. And then by symmetry, it just drops down exactly the same way, right? And doesn't matter which angle you do that integral from, you're going to get the same projection, right? Because it's circularly symmetric. So what does it look like after you convolve it with the inverse Fourier transform of the ramp function? It looks like this, right? So this is our G star L theta. This was the original G L theta. Those don't look at all the same, right? So you can see there's a lot of difference between back projecting these functions and back projecting these functions. Couple of features. One, here is a flat top. We know this is a disk and it should be flat across one whole area. So that's good news, right? That it actually produces a function that has a flat top that we can back project. Secondly, it has these negative side lobes. And remember how we built up all of that signal outside our object with those naive back projections? We had all that stuff out there. Well, these side lobes will subtract all that stuff away, right? And so when we back project these, we get patterns that look like this, and you get a much better looking image with a 0 background. Here, this is wait a minute. How do I get this off? Yeah, this is a movie, but I don't seem to be. There we go. Okay. So this is going to be back projection through a 2D rectangle, right? And what we're doing is we're just back projecting those integrals. You can see the function here, and it adds up to this function. Okay, we'll do that one more time. So here's the integral, these are the GL thetas, right? This is the back projection of those, or you can see the projection. And then here, this is adding them all up with that naive summation or a luminogram, right? And instead of doing that now, let's look at adding up these G star L theta functions, right? Which we have convolved with the inverse Fourier transform of the ramp to get these, right? They look quite different, right? And then as we add those up, you can see the object starts to come into focus. And so now we have a much better representation, right, of our object. There still can be artifacts because you haven't got enough samples or the number of views is too low, et cetera. So you can, in this simulation, when we have objects and take the Fourier transform, you can write a simulation for this in MATLAB in literally one sentence into ChatGPT-4, right? And it will create this simulation for you. And take a look at how this works out. Going back to this example, where we had this complex pattern, this was the GL theta we looked at. This is what G star L theta looks like in that case. This is GL theta, G star L theta. We also have a 0 background here, and these things go negative as well. We back project these G star L thetas to get this. Remember in the first one, it was 0 back here. Here it's got positive and negative on the signal. And here's with 40 projections, 80 projections, 120, and then 240, we get back the object, basically. Okay. So one of the things about this method is that the ramp function, which is analytically the function that comes out of the derivation that you should use to get the perfect object, right? It just came out of the Jacobian for that inverse Fourier transform in polar coordinates, right? So that is the function you should use, and this is what it looks like, right? This is Fourier space, right? In, cycles per millimeter, cycles per centimeter. And for those of you who design filters and you think about the frequency, performance, frequency, bandwidth of a filter, does this look like a good filter? If you've ever done any kind of filter building, this looks like a terrible filter, right? And there's a couple of reasons. One is that you have this super sharp edge where it goes from very high amplification of high spatial frequencies to elimination of high spatial frequencies after you cross over a certain point. Okay? So that is a problem, right? If you actually have data up here, right, and it's getting amplified up, right, then you will see artifacts associated with this very hard edge of the filter. And sometimes our object doesn't have spatial frequencies up there, right? And so maybe the object signal is decaying away, and that's okay. So this boundary isn't a big deal. However, what do we have out at all frequencies? We've got noise, right? So the noise basically has a very broad bandwidth. And so you will amplify noise incredibly by multiplying by this filter. You're saying, oh, all my points up here are being weighted very heavily in my image reconstruction. They're principally noise, right? So you're just going to get a bunch of noise on top of your image, right? And so a number of attempts have been made to make this filter behave in a more user-friendly fashion, so you don't have to look through a lot of noise, right? First off, the first thing that was done is, well, let's roll this filter off such that it doesn't have a uniform slope that just instantaneously changes its direction, right? Let's roll the slope to 0 and then cut it off, right? So that, and this is called a cosine filter. A Shep-Logan filter is this equation up here, right? Which rolls it even steeper towards 0 as you're getting to the cutoff frequency. And then another filter says, you know what? I'm not even going to let this happen. I'm going to roll up to a certain frequency bandwidth. And then after that, I'm just going to start attenuating these higher frequencies until they're gone. And I know all the noise is gone at that frequency because I've brought the filter back down to 0. This is called a Hamming function, where we're kind of doing the same thing, but we don't get all the way to 0 here. And this is a Hanning, which is very confusing, right? You have a Hamming filter and a Hanning filter. And this one is really severe in that it not only rolls down to 0, but it makes the derivative roll down to 0 as you're getting there, right? So it has a real smooth landing at 0, right? So these are used a lot in modern CT reconstruction in order to soften up the image in the sense that you don't get really radical noise features. It does obviously blur some edges, right? So here, this is the Romlock or ramp filter. This on the same data is the Hanning filter. You know, it's rolling to 0 here. And these are the two images that result from that. So you can see the edge here is very sharp, right? It's a really tight edge, whereas here it goes across a few pixels. It gets blurred out, right? So this image is blurrier. This is sharper, but there are some artifacts that are kicking off this thing here at edges. If you look at real data from our scanner, where you have not just mathematical signals like in MATLAB, you also have noise from the electronics and photon counting and stuff like that. So here is basically this is called a bone filter. And it's essentially a Romlock or a ramp filter. It's attenuated a little bit, but actually the manufacturer won't tell you exactly what they do because it's, you know, these filters became very valuable in the early days of CT, and the habit of keeping them secret just stayed in the industry. So they won't tell you the exact coefficients for a filter like this. They'll just say it's a bone filter, and this is a standard filter, and this is a smoother filter, etc. So this is what this object looks like with the bone filter. And you can see there are artifacts at the edge of the object in that there's this ringing artifact. This is called Gibbs ringing, where if you cut off a frequency really sharply at a specific point, anything close to that point, like an edge or something that needs those high frequencies, will give you this artifactual signal, right, from that ringing. And then when you use like a Hanning filter, those artifacts are diminished a lot. And so this is usually the type of filter that radiologists want to see. They don't usually want to look through this stuff. So they don't use the Romlock unless they're doing something very specific. Like I need to detect, you know, something really sharp. I will put up with the noise in order to try and find that thing. And there you can see what it's doing down in at the baseline, just outside the phantom, whereas this one, all of that artifact is kind of smushed out, right? These filters are obviously applied digitally or discretely, right? So you have 800 points, or say 892 or something points in your projection along L, right? And then when you run a convolution across that, you have to decide what are the coefficients for the kernel that is going to be run across that for that convolution, right? And so that takes you to, you know, the nuts and bolts of, well, if these are my, you know, sample points, I need to put the actual values for this filter along those sample points. And so here's a picture of what that looks like for if you're going to do a convolution with the ramp filter. This is what the coefficients will look like. Shep-Logan, the black line is what the coefficients would look like. Hamming and Blackman we didn't look at, but the Hamming we did look at. So you can see it gets, essentially what happens is it gets a little broader, right, as you soften up the high frequencies. And so here's an example of if I had a rect function, that picture I showed you, and you convolve that, this is the function that we're going to be back projecting. Okay, so this is the G star L theta after convolution, right? Here's our input function after convolution. These are the functions we are back project, right, to get the picture. Right? And so here you can see there's very sharp edges, and you can see how we could get edge effects, right? With that, there's like little bat ears on that thing as we're convolving through. Okay. I believe where are we at? 3. Okay, good. We're catching up a little bit. But I need to be here. And PowerPoint. That was part 2. Let's go to part 3. Okay. All right. What we're going to look at now is how things can go wrong. So that's this slide here. Okay. And I'll put all these slides together in one lecture before they're uploaded. Okay, so here's a projection, and this is the detector orientation is down here. This is a particular angle. We've done the integrals to get the projection of the object, and this is the GL theta for some direction theta. Here's the filtered projection. This is G star L theta. Okay, and we're going to back project that to get our object. Okay, and it produces a really nice picture. What happens if we have a untoward event? So we're taking our data, and a spark goes off somewhere, right, and is detected in a few detectors for just one view, right? So we go along, and then at a couple of our detector elements, we get a little blip, right, in just one view, right? And so this is, you could think of this, it's not really noise because it's not sort of a constant random process. It's an artifactual signal that has been injected in there by some process, right? Maybe there's static electricity or something in there. So it's a very small change in the integral through this line. So it's a 10% change in that integral, right? Occurred, and it occurred in one view. When you convolve this to get your G star L theta, if you convolve it with a ramp function, this is the thing that comes out, right? And so because these are very sharp, right, you get an amplification with that ramp filter of high frequency objects or really sharp changes in the pixels. And so that's what the view looks like, this view. And we can say all the rest of the views are fine. They didn't suffer from this injection of bad signal or artifact. When you reconstruct the image, it's pretty simple to see what happens, right? You're going to get 3 distinct lines through here because they're back projected with that. After this convolution, we back project this thing, right? So you get these 3 very distinct lines, and those are called streaks. And it's a very common artifact in CT because of the way this reconstruction is done to see streaks running through your image. It's a lot of artifactual processes make these little peaks that turn up as a streak, right? So here, same thing. If a 10% error is added, not at one channel, but a set of channels, it's a different process, right? Because when you convolve this function, you get something that is a lot softer. It's not super high because it was so sharp, right? But it's still, in one of these views, and you're going to get a projection back through that's a dark streak through the image, right? That view. So now let's see what happens if you have a 1% error in one of the detectors. So it's barely visible in the integral, right? So this one of these detectors has a 1% change in the integration of that signal. So it's, for whatever reason, let's say the gain of that detector dropped, got old, and the gain dropped a little bit, right, by 1%, right? But that detector is always 1% down, right? So then every view has a 1% reduction in the signal. And what does that look like? When you do the convolution with the inverse Fourier transform of the ramp, it peaks its little head up, right? That 1%, because it's one channel, right? And then it's on every darn view, right? That you back project. And so it looks like a circle in the image. And these things you can't get rid of. Even when you calibrate the scanner, when you get down to really, really low numbers of photons and you look at the center of your image, you see these faint circles, right? Because to calibrate the detectors so that they're right on the money every time and not just a little bit off for their gain is really difficult. That's why they calibrate these things every day, right? Because these small percentages that are constant, right, are a source of these strange artifacts, right? So you'll see this towards the center often where you have really low signals. We can look at the effects. So let's, before we go here, are there any overall questions for that? So we went through a lot of stuff. The projection slice theorem was required, right? It's kind of a miracle theorem in that you have a continuous object, integrate projections down. So now I have a 1D representation of that 2D object, which is just the projection at a specific angle. I take the Fourier transform of that function, and it turns out to be a sample through the Fourier transform of the 2D function. That's the projection slice theorem. That's fundamental to why CT can work at all. And it's, you can try and come up with a heuristic explanation of why that works. If anyone can do that, would be great, because I'll use it from here on. But I don't know one. Okay. Yeah.
So when you take the Fourier transform of G of L, which is like the sum of all those new values at those specific points, when you take the Fourier transform of that, that's a sample through the already existing 2D projection.
It's a sample through the 2D Fourier transform of your image or of your object. So here's my object. God-given 2D Fourier transform of that object is over here. We don't know what that is. Okay. We don't even know what the object is. All we know is the projections through that object give us this 1D function. I take the 1D Fourier transform, and it turns out, and now I know one line through the Fourier transform of my object.
Okay. And then so when we inverse Fourier transform that, that's when we get the convolution.
Yeah, so let's say I just keep doing that process. You got it to the line, right? So now I just change that line a little bit, do it again, change the line a little bit, do it again. Take 1,000 lines through the Fourier transform of the object. Now I've got a lot of points. So I should know what that Fourier transform of the object is, right? With all those points, right? So they're in polar coordinates. So we take the inverse Fourier transform of that data now, and it gives me the object or an estimate of the object. To do that inverse Fourier transform, because they were measured in polar coordinates, I need to use polar coordinates in that inverse Fourier transform. That's where that absolute value of k comes in, because that is basically the Jacobian of that integral, right? For that integration. So boop, I come back, and now that inverse Fourier transform gives me my object or an estimate of my object.
And so those filters we were just going through, is that like the k, the inverse of the k?
Yeah, the filters we're going through are, if I take the function absolute value of k which is basically it's zero at the origin and just goes out linearly in all directions, right? If I take the inverse Fourier transform of that, I get some function over here, right? And that you can convolve GL theta directly with that and add all those things up to make a picture. The problem with it is that, as we saw, high frequency objects get amplified, a lot. And so if you don't have beautiful fidelity in your data, that convolution will cause big artifacts. And so that's why we went through all of this way. Well, what's a better filter? So it's not the pure Jacobian anymore. It's the Jacobian times some filter to try and bring down the high frequencies a little bit.
Oh, so you're introducing a filter into the Jacobian.
Yeah, or into that integral. Right.
Okay.
Yeah. Right. Okay. So, well, here it is right here, right? So here's our object, right? That we're trying to get. We've got these samples of the Fourier transform of our object, right? By that slice projection theorem. And so what affects basically the sharpness or the resolution of our estimate of the object? Well, we know that if let's take these two terms out, and I have the ramp here. Sorry, this is from the book. This would be absolute value of K. We know what that, ideally, if my spatial frequency of this thing is bounded, so it goes down to 0, I could just integrate out until that happened, and then the whole thing would roll off, right? I'd be fine. It's usually not the case. So we do a couple of things. We introduce a filter, which is right here, right? And that's that Hamming, Hanning, cosine, all those filters we went through, and that rolls the signal off in Fourier space at high frequencies, right? So that affects our spatial resolution. This is another feature, which is the detector blur. And so basically our detectors aren't infinitely close together, right? So there's a certain spatial frequency we can estimate, and beyond that, we can't estimate anymore because the detectors aren't close enough together, right? So that is a feature that basically goes into your estimate of what your spatial resolution will be, right? And then there's one other thing that is not in this formula in the book, and that is when I look at where my X-rays are coming from, and I basically look in my detector and look back at the source, right? If the source was a point, then I wouldn't have any blurring because of due to the source. The source isn't a point, and so you can think of the source as let's think of it as a 16 by 16 array of much smaller sources. So each one of those little sources you can think of as a point, right? And now my image is actually a sum of all the images from those points, right? And so those images are slightly shifted with respect to each other, right? So if I look back at my spot and it's a rectangle, photons from the top left corner of the spot and photons from the bottom right corner, they will give me an image on my detector that is just shifted just a little bit, right? And so when you add all those up, that gives you a blur. And so that's spot size blur. For many applications, it's not a big deal. For some applications, it is, and you want to make the smallest spot size possible. The problem with that is you run out of X-rays, right? As you make the spot size smaller, you can only get a finite number of X-rays out. If the patient is very large, you're just not going to get any photons on your detector. This is fine for really skinny patients. You can use tiny spot sizes, right? And this is like in Japan, they came up with a new CT scanner that has twice as many detector elements. So they reduce the size of a detector element from 1 by 1 to literally 0.5 by 0.5, right? So now you've got basically 4 times as many detector elements. But in order to cash in on that increased resolution, you need a spot size which is also commensurately smaller, right? Luckily, most of the people in Japan, right, are in much better shape than the people here, right? And they actually have, smaller body habitus, and so it's not a big deal. Here, you run out of photons, right, for half the people, right? So it becomes an issue. Yeah.
But if it just increases scanning time, so
You can increase the scanning time to integrate the photons up, absolutely. However, do you stay still? Right? So basically, if you have to integrate up, then eventually the person moves, right? So that's the issue. Okay, so I think we're good, right? I think that was time. Okay, so I was going into the point spread function, which we have looked at before, but we'll start here on Wednesday. Yeah, one quick. Oh, that's a great question. It depends, obviously, on the size of the detector, right? So, okay, so here's an open problem for you a little bit. If my detector is, say, a square, and it's 1 by 1 millimeter, what is S of K? That's the open question. We'll talk about it next time. Okay. So I gave you what it is in space. You got to figure out what it is in Fourier space. Okay.